I should say, just as a point of amusing trivia, I took German in high school like 15 years ago, so I can almost pronounce Hochreiter and Schmidhuber. I cannot read that well enough to read that German paper, right? Pronouncing their name hopefully correctly is about as deep as my mastery of German goes. So what is a gate unit? So a gate unit is a unit that learns to manage the flow of information. Blah. So two important parts. One is this sigmoid, right? That is the logistic sigmoid, which looks kind of like tanh, but it has a range of 0 to 1, right? So a gate unit, basically, So, okay. G, basically, is going to be a column vector, the way that we've been notating these things, that is going to be full of values between 0 and 1, right? So we look at, so here, if we're kind of treating this as the structure of a gate unit, we look with we learn to look at the input, just like any other unit does, and we map that to a bunch of values between 0 and 1. Then, this is pointwise multiplication, right? We multiply something we care about by that list of gates, right? So what we basically do is we filter it, right? Each term in the input is going to have a corresponding sort of gate unit that is going to get a value between 0 and 1. And when we multiply it, if the value is near 1, it will not filter that channel, right? It will let that through. So if it learns to produce, under some conditions, a value of 1 for a certain gate, right, then when we do this pointwise multiplication, it will let that value in unmodified. Other times, let's make those, there we go, right, if it learns to have a value of 0 on a certain channel, then when we do this pointwise multiplication, it will multiply that x by 0, and it will block it, right? So what O here ends up being is some things from the original input roughly unfiltered, right? And then other things from the original input blocked out, right? Multiplied by something near 0. So what it is learning to do is function as a gate, right? To let some parts of x through sometimes and block other parts of x other times. We also use sort of these constant error carousels / memory cells, okay? And the update, so the update rule for the memory cells is f, which is a forget gate, times the previous time step's cell value, plus I, which is the ignore gate, times a candidate next cell that we compute, okay? So C of t minus 1 is the previous cell state. C hat of t is a candidate next cell state. And to come up with our next cell state, what we do is we filter some of the old cell state through a forget gate. So we choose to forget some of it and remember the rest of it. And then we filter the next candidate cell through an ignore gate. We learn to filter some of it, right? To ignore some of it and to accept the rest of it. And then we add them together, right? And this is where the constant error carousel comes through, right? Because the derivative of that is 1, right? I mean, saying the derivative of plus is 1 is not technically correct, but sort of we are not multiplying these by repeating weights, right? And we're not passing them through a squashing activation function, right? This thing just goes through some scalar multiplication with derivative 1, and then addition, and then this thing, So basically this thing just goes through a scalar multiplication with derivative 1, and then an addition with another thing, which is derivative 0, right? So it's constant error, right? Derivative 1, basically. As we go from time step to time step, those don't get passed through a squashing activation function, and they don't get multiplied by a weight, right? They're just gated and added over and over and over again. And these memory cells, right, these constant error carousels just kind of serve as a line through time that allows information to just pass through continuously, right? As long as it's not blocked by a forget gate or overwritten by something that doesn't get ignored, right? So LSTMs have a fairly complicated internal structure. You will see pictures like this one a lot. I got this one, like a couple of other things, from the Wikipedia page. Largely, I mean, no insult to these fine gentlemen who provided this thing, right? And thank you to them, but largely just because it's copyleft, right? Like everything in Wikimedia Commons, it's copyleft. So if you look at this, you might be sort of confused and slightly despair of figuring out the dynamics of these things. Basically, the important bits, we have the error, or we have the memory cells / constant error carousels, right? This thing is the constant error carousel. But we have the memory cells as sort of a line through time up top, and then we have the hidden state as sort of a line through time on the bottom, but the hidden state is getting a nonlinearity applied to it. And the hidden state is the thing that serves as the output, all right? So we have the cell state, and then we have the hidden state. The hidden state is the thing that gets the nonlinearity, and the hidden state is what the rest of the network sees as the output of this unit. So I think the math is a lot simpler, frankly. So you could kind of, at least, I don't know if you're a more visual learner than I am. I do not get very much insight from staring at this picture. If you know how to read matrix multiplication, even though this is dense, it is also perfectly clear and straightforward, okay? And if you're looking at this, right, this is part of the reason that we did a bunch of matrix math early on, right? The more you get into non-trivial neural network layouts, the more looking at the matrix math is going to far and away be the easiest way to understand what's going on, right? Hopefully, if you'd like to hopefully you think it was worth it, right? Hopefully you're looking at this going, yeah, I can understand that. And then hopefully you're thinking, wow, I'm glad we practiced with this a bunch. I hope, right? If not, don't worry. We will break this down very, very slowly, because if you sort of think of it as a bunch of steps like a program, it's not really that hard to follow. So first, with this f of t, we're going to get the forget gates, right? Notice that the math for figuring out the forget gate looks pretty much like a normal neural network forward pass, right? We have a weight and an input, plus another weight matrix and another input, plus a bias, right? We have one set of weights for the input at time t, and another set of weights for the hidden state at time t minus 1. So the previous hidden state, right? Current input, previous hidden state. Notice that those don't have to be the same size, right? They have to have the same output size because we're adding them, but the input and the hidden state do not have to have the same size as inputs, right? They can be different. So first we find the forget gates, then we find the ignore gates, which has the exact same structure, right? Its own weight matrices, right? But one connected to the input at time t, that's supposed to be a t, and one connected to the input from the previous time, t minus 1. Then we compute the output gates, right, which have the same structure, right? One set of weights for the input at time t, one set of weights for the output at time, for the hidden state at time t minus 1. Now that we're armed with our forget, ignore, and output gates, we can find our candidate cell state. So the candidate cell state is tan h. These are sigmoid, right? The output gates use sigmoid nonlinearity. The candidate cell state uses tan h nonlinearity. By convention, you could use a different one. TensorFlow allows you to use, for example, ELU there if you want to. But by convention, we're going to use tan h. And again, we have one set that connects the candidate cell to the current input, another set of weights that connects it to the previous hidden state, and some biases. Then we get our next cell state, right? So then our next cell state is the forget gate times the previous cell state, right? So we filter the previous cells to the forget gate, plus the ignore gate times our candidate. So we filter our candidate through the ignore gate. And then finally, now that we have our current cell state, we output tan H times the cell state, or I'm sorry, tan H applied to the cell state, filtered through the output gate, right? So the hidden state can store values that don't get outputted because we are filtering the hidden state through the output gate, right? So the hidden state and the cell state do need to be the same size, right? Because like this is not getting resized here, but we do not have to allow everything in the cell to go into the hidden state because we can choose to filter it with the output, right? So we can have things in the cells that the rest of the network doesn't have to learn to ignore because we have this ability to filter the cells before they go into the hidden state. Okay? It's complicated. It is decidedly complicated. But, so, yeah. Find the forget gate, find the ignore gate, find the output gate, get your candidate cell state, compute your next cell state by filtering through the forget and ignore gates, compute your next hidden/output state by filtering through the output gate. All right? Find your gates, find your candidate, get your official, right, filtered one, and then get your output state. So there are many, many variations and modifications of LSTM. In some version of these slides, I mentioned that LSTMs originated in 1998, I think. They've been around for a while, right? And I think I described them as evergreen because they were introduced when I was still in high school and are still used in a lot of state-of-the-art results, right? And they are like convo nets in that way. CNNs also date from the late 90s, and convolutional layers are also still used in many state-of-the-art results. But one of the prices here, the fact that LSTMs have been around so long, relatively speaking, is that there are many different variants of them. People have subtly modified these things over the intervening years. People have subtly modified these things over the intervening years. Best practices have changed. Architectures have shifted subtly. And we are once again at the point where saying LSTM can mean slightly different things to different people. Okay? So it's sort of like people say LSTM like it's one thing that everybody agrees what it means, and that's not really true. All right? I believe it is true. So if... Okay, so the original, one notable thing is that the original paper didn't use full backprop through time, right? And I seem to recall them saying something like that LSTMs were so effective at remembering things that you could truncate the history in BPTT to 1, right? So they basically didn't need a history, was claimed at one point. I think that is no longer considered best practice. A later paper basically said, hey, you can use full BPTT with these things, full backprop through time, and that works better. And so now I believe best practice is to store all of the states and unroll them in time basically the same way an RNN does. All right? So people have also, I think it is also true, and I'm not going to swear to this, but I think it is true that the forget gates were not in the original paper. I think those were added later, right? So I think there's another paper called The Importance of Learning to Forget, something like that, that introduced those and proved they were important, right? So I think that's another addition that's sort of made traditionally that isn't in the first paper. You'll also see a bunch of variants. So you'll notice, that several of these steps is kind of like a whole layer, right? This, and this look like the entire forward pass math for a layer, right? That's a lot of math cost, right? And I mean, also notice that this is across two sets of inputs, right? An input and then a loop from the hidden layer. That is a lot of math. So a lot of people have sort of tried to simplify these things. There have been various modifications that, merge some gates, drop some gates, whatever, The gated recurrent unit is a particularly popular one that, again, if memory serves, merges or omits several gates. However, it has later been pointed out that many of these simplified networks do not outperform the LSTM and sometimes underperform it, right? It turns out that when you start removing some of these gates, these networks lose the ability to learn on certain problems, okay? And again, we're talking about training power here, right? RNNs and LSTMs, right, actually have the same theoretical compute power, right? For any problem an LSTM can solve, there exists a normal vanilla RNN that can solve it. It's just that RNNs can't practically be trained on many, many problems that LSTMs can easily be trained on. It is like that to a lesser degree between the LSTM and some of its simplifications like the GRU, right? The GRU, or GRU, has the same sort of theoretical compute power as the LSTM, right? The classes of problems they can solve are the same, but there are a few problems on which LSTMs can train that GRUs cannot. And I think, if memory serves, it's counting. I have read, not in a formal publication, but I've heard, that GRUs cannot learn to solve rules, or they have to learn to count, basically. So if you wanted it to output the number of like a particular input pattern, it would struggle to learn to do that. So it turns out that all of the gates that are in conventional full LSTMs actually kind of do something. And when you start removing those or tying them, you start to lose a little bit of training power, right? That means that for all the research work that has gone into these things, vanilla LSTMs, right, are still a pretty dominant architecture, right? They're still used in a lot of things, right? And again, things like GPT-3, right, which is that giant OpenAI language corpus, or AlphaStar, right, which is the StarCraft playing agent. Both of these things still have, I believe, so it says LSTM, I think that means vanilla LSTM, right? Still have, a bunch of this in them, right? Both of AlphaStar and GPT-3, I think, internally still have a bunch of sequence processing LSTMs, right? Brief video break.